Hello and welcome to the third video of the FP2 chapter, Polar Coordinates. On the screen, a quick starter. Don't actually sketch these graphs, but if you've got time, pause the video and think about how you would go about sketching each of these graphs. For example, this one here, you might just take the y-intercept and then do a slightly downward sloping line, or you might find the y-intercept and the x-intercept and connect them. This one, you might know what the general shape of this is. With the y-intercept here, just put it on roughly. Perhaps you would work out the roots first. Here, maybe you would think about the y equals x cubed graph and then translate it. Here, similar idea, you might think about the cos graph and then just apply transformations. This is one you might know, roughly. But this one here, out of all of them, this one might be a bit of a problem. And if you don't know how to sketch this, as you probably don't, I don't, then at the very least what you can do is put some values of x into this equation, find their corresponding y values, plot a few points until you get enough of a graph to sketch the remainder. In this case, it's quite complicated. In this video, we're going to sketch polar curves. And as that starter might make you think, a reliable way to sketch a graph is simply to calculate a few points and plot them. In this chapter, if you've got any doubts, do this. Just calculate a few points and plot it, and then build up your sketch around those points. But keep in mind that for polar curves, r must be equal or greater than 0 because r is the radius, it's a distance. So if you get any regions where r is less than 0, which can happen with the sorts of graphs we're looking at, don't sketch them. This is particularly important to remember because if you've got a graphing app of some sort that you use to help you do these, or to understand them, your graphing app will probably sketch these regions by taking the absolute value of r. So plotting some of these graphs on a graphing app will make them look very different to what your examiner will expect you to plot in an exam. Where r is less than 0, do not sketch those sections. So, if in doubt, plot a few points, ignoring any where r is less than 0. However, you should be familiar with a few standard polar functions, and the more familiar you are with these, the less likely you'll have to stop and plot a whole load of points. So a few to look at here: r equals a, theta equals alpha. We have done these in previous videos, so we won't spend long on these two. Then r equals a theta, r equals a sine or cosine n theta, and r equals a times p plus q sine theta or p plus q cosine theta. We'll look at each of these in turn. So r equals a, that is just a circle. The radius is a fixed constant, circle with center 0, 0, and radius a. We did that one before. Theta equals alpha, a half line through 0, 0 at an angle alpha with the initial line, like this. I should clarify here that when I say through 0, 0, what I mean is it kind of starts here, but it does not actually include the pole. So you have a little open circle on the pole there, and then a line coming off of it. The third one of the new ones, r equals a theta. So here I'll take a moment and do what I said on a previous screen. If you're not sure how this looks, you can just go ahead, find a few points, and plot them. So here we've got theta as our input, r as our output. So if we take 0, a times 0 of course is 0. And then a few different angles. So let's go around the circle. We want maybe pi by 2. And if we times that by a, whatever a is, we get a pi by 2. So r is bigger. And then if we take pi, times that by a, we get a pi, it's bigger still. And then 3 pi by 2, 3a pi by 2. And then 2 pi, 2a pi. So it's getting bigger and bigger as theta gets bigger. Sketching this, with theta equals 0 over here, pi by 2 here, pi here, 3 pi by 2 here, and of course 2 pi over here, and then If you were to continue this, getting bigger and bigger, you would just go round and round again and again. Here we've got something interesting happening. At theta equals 0, initially we've got no radius. We're at the 0 point. But when theta is pi by 2, the radius has increased to a times pi by 2. So of course this depends on a, but we can just write a pi by 2. And as we come around, so that was from this line, theta equals 0, to this line coming around here, as the angle increases to pi, the radius has increased to a pi. So whatever a is, it's now about here. And as we continue around to 3 pi by 2, it's increased again. And continue around to 2 pi, it's increased, it's now 2a pi. And you can follow this pattern as you continue round. The r value will increase as the theta value increases. So as you keep going around and around, your radius gets bigger and bigger and bigger. And what this creates is a nice spiral. So I've got a better picture here. Spiral starting at 0, 0. I'll clear this off so you can see that. This is a spiral starting at 0, 0. And of course the curvature of the spiral depends on the a value. For the remaining ones, I won't go through that process of plotting points, but I hope you can see that you can always do that if you're ever unsure what a graph should look like. Number 4, a little bit more complicated. R equals a sine n theta and r equals a cosine n theta. I'm going to switch over to a graphing app so we can see what this looks like before I put a summary on this screen here. Here we are with a polar graph. We've got r equals a sine n theta on the screen at the moment in purple. I've set a as 4 and n is currently a 1. So this is 4 sine theta, which is something we did in our previous video, just a circle moved up on the y-axis. Now if I increase n from 1 to 2, you can see what has happened here is we've got 2 loops. We have a loop in the first quadrant and in the third quadrant. And that's because of this little bit I've put on the end here. R is greater than 0. Now I had to specify that in this app, otherwise it would have plotted all of the r's greater or less than 0 as if they were greater than 0. But this explains why we've got 2 loops in 2 sections, because these are the 2 sections for sine 2 theta, where sine 2 theta is positive. The first quadrant and the third quadrant. If it was just a 1, as we saw, then we know sine theta is positive in these 2 quadrants, but as you increase that to 2 theta, then it's positive in the first quadrant, negative in the second quadrant, and then you get your repetition, positive in the third quadrant, negative in the fourth quadrant. And if I increase that again, we see the same thing happening. Now we've got 3 cycles, and you can see that it's positive in the first section, the first of 6 sections, from 0 to pi by 3, and then from pi by 3 to 2 pi by 3 it's negative. That's one cycle of the sine function. And then from 2 pi by 3 to pi it's positive, and then it's negative, so there's nothing in the next section. In the 5th section it's positive down the negative y-axis, as it were, and in the final section it's negative, so there's no curve. And we can do this as many times as we like. Each time we are introducing an extra loop. And you can see that every time in the first section of the sine cycle there is a graph, and in the second section of the sine cycle there is no graph because r would be negative. The number of loops you can see corresponds to the n value. N equals 5, 5 loops. Okay, let's take that back down to 1 and put cosine on. Now it's very similar here, except we're kind of focused on the positive x-axis, because this is where our cosine curve starts, and you know that cosine is symmetrical, so it's positive either side of the 0 angle, from 0 to pi by 2, and from 0 to negative pi by 2, which is why it straddles the axis here. And as we increase this n to 2, something similar but slightly different happens. We've got 4 sections again, and it gives a positive value in that first section straddling the positive x-axis, and then from pi by 4 to 3 pi by 4, the section straddling the positive y-axis, there's no graph because that's where r would be a negative value. And then it repeats. We get the positive value and a negative value again. So 2 full cycles. And as you can see, if we increase this to 3, we get 3 full cycles. Again, straddling the positive x-axis because of the way the cosine function works. It's symmetrical about the y-axis if you plot it on an xy graph. And if we keep increasing that, you can see the same thing happens. The number of loops that we have corresponds to the n value. In this case, it doesn't move around in quite the same way because every time you have a cosine curve like this, it will have one loop straddling the positive x-axis, or the theta equals 0 initial line. So if we compare that on the cosine and jump back to sine for a second, just to compare them, you can see instead of having a symmetry about the initial line, this is always slightly off symmetry about the initial line. I hope that's enough for you to understand my little summary here, which is that we have n loops with one loop in each region where r is greater than 0. The maximum distance from 0, 0 for each loop is a. So this point from here to here, this distance is a. From here going out radially to this distance is a, and so is this. In this case, a is a 1, and it's cosine 3 theta, so we have 3 loops. Here where r is positive, here r would be negative, so we don't sketch it, even though some apps would. Here again, on the second cycle, r is positive, r would be negative, and on the third cycle, r is positive, r would be negative. Similar for the sine, a is 1 here, sine 3 theta, r is positive, here r would be negative, so we don't sketch it, r is positive, r would be negative in the second cycle, and in the third cycle, positive, negative. So once you get used to the pattern of drawing these, they become quite standard. Here we have a couple of examples then. Sketch the polar curves for the equations r equals a sine 4 theta. So I need 4 loops. So I'm going to split this into 8 sections, where down here theta equals 0. And I know sine is positive in the first section. So here we have a loop, and then we won't. And then here we will, and then we won't. Here we will, then we won't, and here we will. And each of these, although I haven't drawn it very accurately, each of these is a. If we had r equals cosine 2 theta, then we would have one big loop here, and one big loop here, but you can see there's something slightly different going on here. We've got r squared equals a squared cos 2 theta. Now the way to approach this is to square root everything. We get r equals a square root of cosine 2 theta, and because r must be a positive value, we don't need to worry about a plus minus on this. All we need to do is consider what does the square root of cos 2 theta look like compared to cos 2 theta. And you know that cos 2 theta is less than or equal to 1, therefore the square root of cos 2 theta is not only also less than or equal to 1, but greater than or equal to cos 2 theta, because when you square root a decimal, it gets bigger. What that means is just a slight difference to the shape of the loop. Everything else stays the same. So we need 4 sections to this graph, but not these 4 like this, because it's a cosine curve. It's going to actually be these 4. So this will be the first section where there will be a loop. Let me put that on. And then here there won't be a loop, and then here there will. And here there won't. But I just said we need to change the shape slightly, and it's because the square root of this is going to be bigger than this. And all that does is it rounds out the loop a little bit more. So we get a slightly rounder loop. And if your drawing skills are like mine, it might be difficult to tell which ones are rounded and not. But there we go. And again, this distance here is a. So a slightly more accurate view of that. Here we go. As with cosine 2 theta, which we just did on the screen there, sine 2 theta is less than 1 or equal to 1, which means sine 2 theta must be less than or equal to the square root of sine 2 theta. So if we have a sine 2 theta with an r squared and an a squared, just like we had with the cos 2 theta, it's a slightly rounder loop. And here is a more accurate depiction of that. Here we've got a sine 2 theta, and here is r squared equals a squared sine 2 theta, slightly rounder, as you can see. Okay, that's quite a lot on that type. Let's move on to the fifth and final type, which are these two here. Now again, to show you what's going on here rather than just ploughing into the notes, I'm going to go back to the graphing app and we can see exactly what's happening with A, P and Q. So here in red, I'm starting with r equals a times p plus q cos theta. And again, I need to specify here that r must be greater than 0. Otherwise, the graphing app will do something with the negative values of r, which we'll talk about very briefly in a minute. I've set a equals 2, and you can see that at the moment p is 1, q is 0. So the equation with these values is just r equals 2, and you can see that that's a circle on the screen as you would expect. But if I make q bigger than 0, then we have this cosine theta term coming in, and you can see that something funny goes on. It moves off slightly to the positive x direction, and as q gets closer and closer to the value of p, not necessarily the value of 1 as it is here, but the value of p, we end up with a little dimple coming into the curve. And when q is equal to the value of p, in this case both are equal to 1, we get what's called a cusp. Now if we zoom in here, you can see that this is not a continuous gradient. There's an instantaneous change of gradient in here. If I take that out again slightly, you can see here is a nice smooth curve, but as we get here, it's not. If I were to keep going, you can see it continues to be a cusp. And actually, we don't need to worry about a situation where q is bigger than p, but we will talk about that again in a second. If I bring it all the way down again, and bring it the other direction, you can see that if q is negative, we get something very similar just happening in the other direction. Okay, there are 3 key points to note here. The first is that situation with a cusp where p equals q. If p equals q, this will always happen. Now if p is bigger than q, but not twice as big, then you'll get this nice dimple shape coming in here. If p is twice as big as q, the dimple shape disappears. And if it is bigger than that, you can see it just kind of rounds out, almost like an egg shape. But you can see that it's not concave like this. It doesn't come in towards the pole. Once p is 2 times bigger than q, it doesn't have that dimple shape. Now if I bring that back to the center and change over to the sine curve, you can see a very similar thing, but in the y direction. If p is equal to q, you get the cusp. If p is bigger than q, but not twice as big, you get a dimple. It's concave. And if p is twice as big or more than q, then it's convex. And you get this sort of generic egg shape. And if it becomes negative, it just goes the other way. Okay, very quickly, I'm going to get rid of the greater than 0 restriction for r to show you what that cusp is all about. So here we've got this, and if I keep going past p is equal to q and make q bigger than p, then this is what's going on. But those bits of the curve in the middle there are where r is less than 0, so you should not sketch those in an exam. But it does explain why there's a cusp there, because if you skip those bits out, if you cut them off, then you end up with a cusp in the middle there with the bits that are left. And I'm sure all of this makes sense to you if you think about the equation. You've got a cosine theta on the initial line when theta is 0, then cosine of theta is a 1, and you just get p plus q times a. That gives you your x-axis intercept. And if you put theta is equal to pi by 2, you get your positive y-intercept, where cosine is 0, and you just get a times p. Same with the negative y-axis, but remember in this case, although I'm calling it the negative y-axis because I can't point at it on the app, it's not actually negative because this is a theta equals 3 pi by 2 line and the radius is still a positive value. So you can see here we've got positive values down here, even though I'm calling it a negative y-axis to help explain where on the graph I'm looking. And when theta equals pi, what we would normally think of as the negative x-axis, then you can see that that's where we have our cusp. And if you put that into the equation here, you can see that that would produce a negative result for r, and that's where we get our cusp coming in. I highly recommend getting a graphing app like this and having a play for yourself. I think it really helps understand what's going on. Back to the notes, and we have our 3 key bits that you need to know. When p equals q, when p is greater than or equal to q and less than 2q, I've included this equal sign here, even though that's the same as this, because this is kind of like a subset of this group here. And when p is greater than or equal to 2q. And we've got names for each of these. This is a cardioid, specifically, which is an example of the dimpled egg shape, as opposed to an egg shape. So the cardioid is where you've got a cusp here. The dimpled egg shape is where this is concave, so it comes in to some degree, and obviously this is also concave, so this is a dimpled egg shape, but it's specifically also called a cardioid because of the cusp there. This is a dimpled egg shape more generally, not a cardioid. And then if it doesn't come in at all, if it's not concave but convex, like this, then it's your egg shape. And these are the 3 scenarios you need to be familiar with. Like I said earlier, if you forget all of this, you can of course just create a table of values, plot a few points, and that should give you a general idea of what's going on in the graph as well. But if you can remember those 3, it makes plotting things like this much easier. Our final examples sketch each of these. So the first one, we've got A is just A, P and Q are both 1, so they're equal, so we have a cardioid. It's a cosine curve, so it's going to be coming out this sort of way, rather than this way. So I'll start my cardioid in the middle, so that I get the cusp nice and clear, and it's kind of heart-shaped. Then have a quick think about your interception points. When theta is 0 along this line, then cos of theta is a 1, so that's 1 plus 1 times a is 2a. So we can label that point as 2a. Along this line, when theta is pi by 2, cos of theta is 0, so that's gone. We just get 1 times a is a. Down here, theta is 3 pi by 2, cos of that is still 0, so we have another 1 times a is a, and again this is a positive because it's radius, not a negative. And in this direction, when theta equals pi, cos of theta is minus 1, and then all of this collapses to 0. The labels on the axes here should be your initial line, theta equals 0. You can put some of the other values on here as well, but this is the important one. Do not label them x and y, because this is a polar sketch. Number 2. Here we have a sine curve, so it's going to be going in this direction rather than this direction. And P is more than 2 times bigger than Q, so we just have an egg shape. So that will look something like this, my terrible drawing, but the key point here is that this section here does not dimple, it does not go in, but continues rounded. Then I can look at my axes, and when theta is 0, we have sine of 0 is 0, r equals 5a. So this is 5a. When theta is pi by 2, sine of theta is 1, so we get 5 plus 2 is 7, 7a. That's why this is further up here. When theta is pi, we get a 0 again, so it's a 5a again, which is why this is symmetrical about what we would normally call the y-axis. And down here, when theta is 3 pi by 2, this is a minus 1, so 5 minus 2 is a 3. We get 3a on the bottom here. Third and final example. Initial line there. This is another cosine curve, so we're going in this direction. P is bigger than Q, but not 2 times bigger. So it's a dimple, but not a cusp, because they're not equal. So it does come in, but not cusp like this. So to get this fairly accurately, I tend to start with this bit here, because this should be symmetrical about the initial line, and then it comes round something like this. Again, key points on your 4 main theta values. When theta is 0, cosine of theta is a 1, so this becomes a 5a. When theta is pi by 2, cosine of that is 0, so this is a 3a, and this will also be a 3a down here. And then when theta is pi, cosine of pi is minus 1, but because these are not equal, this still gives me a positive value. It's just a smaller value than everything else. We get 1a, which is why it's come back in again here. I hope that's clear, and I really hope you have time to investigate this for yourself with the graphing app, because there are some lovely curves that you can get out of polar functions. Cardioids are just one of them, and if you're interested, cardioids come up every day in such a simple way. If you ever have a cup of coffee or a cup of tea, and it's a nice porcelain cup with a bit of light shining through the window, you can probably see a cardioid in your teacup. Isn't that lovely? You can also make cardioids with straight lines. There's a little example here. But there are many, many sorts of graphs you can make with polar functions, far beyond Cartesian equations. Here are just a few examples. And this should be enough for you to practice questions from exercise 8b. Have fun sketching some of these graphs. And maybe I'll see you in the next video.